Okay, so we finish up with Giovanni, who will tell us about the approximability for Lagrangian submanifolds.
Yeah, first of all, thanks for inviting me to speak here. It's a great pleasure. Yes, today I will talk about a joint work that I am doing with my advisor, Paul Biran, and with Octav Cornea, that hopefully will be out soon, about the concept of approximability for spaces of Lagrangian submanifold. So we start here on the left. My setting will be the following. We'll take a symplectic manifold M omega, which is either cotangent bundle with standard exact symplectic form, or the two-sphere, or the two torus. And in it, we will look at classes of embedded Lagrangians with either closed exact Lagrangians contained in some disk bundle, or equators on the sphere, or non-contractible curves on the two torus. And we will denote this space by curly L, and we will endow the space of Lagrangian with the Lagrangian spectral metric, which is which was originally introduced by Viterbo for Hamiltonian diffeomorphism in the 90s, and it was extended to the Lagrangian setting by many people. And the motivating question is, we want to study notions of complexity on this space of Lagrangian, and we would like to understand if there's some kind of finite models at all scales, in a sense that we will explain, and we would like to define like complexity measurements such as entropy for maps on these spaces and so on. And what do we know about these spaces? We know that it's separable and it's in general non-compact, and there is a guiding conjecture due to Viterbo that was formulated for cotangent bundle or tori, but we can extend it to all cotangent bundles. That the diameter of this matrix space is finite. This was proved in some instances by Shulukin, Kislev, and Shulukin. And okay, this is more or less the setting. And okay, we will talk about approximation, and our like abstract setting is that of a metric space, which I will denote X gamma, embedded in another metric space, which I will denote YD. And what you will have to keep in mind for my talk is that X is our space of Lagrangians, gamma is indeed the Lagrangian spectral metric, while Y will be the space of objects of the derived Fukaya category, and D will be some kind of interleaving distance on the derived Fukaya category. So first of all, I will do some topological recalls. So in this situation here, in this abstract situation, we fix an epsilon bigger than 0, and we define an epsilon net of X in Y to be a subset of Y, which I will denote Y epsilon, such that for every point in X, you can find a point in Y epsilon that lies at small distance from it. And as we all know, we say that the metric space X is totally bounded if we can find a finite epsilon net. Okay, like Turing in the 30s introduced a kind of refinement of the concept of totally bounded or total boundedness for metric groups. We will for a moment assume that our X is a metric group, and Turing was calling X to be approximable, if you could find a finite epsilon net that also approximates the group structure of X very closely. So X is approximable if and only if for every epsilon we can find an epsilon net which is a finite group and which has a epsilon close multiplication to that of X.
Sorry, what is metric group? Is B invariant, left invariant?
Yeah, this we assume, yes, sorry.
So you assume what?
I assume that it's left invariant.
Left invariant, I see.
That the metric is left invariant with respect to the group structure. Yes, and Turing was able to show that if you have a Lie group, this is is approximable in this sense, then it has to be compact and abelian, so not many cases. And we have also a slight relaxation of Turing approximation that instead of assuming that our epsilon nets are a finite group, we will only assume that they are finitely generated. And this is a bit more or less, this is more in line with what we will describe now. So what we try to do is to like introduce on our spaces of Lagrangian a notion that it's inspired by this Turing approximability and is a bit a relaxation of being totally bounded. And this goes abstractly as follows. So we assume that there is a triangulated persistent category C, and here we can forget for a moment the word persistence and think only to a triangulated category, such that its set of objects is Y, which in our mind is like what it should be, the objects of the derived Fukaya category. And the metric D is the interleaving distance. And we say that our metric space X is categorically metric approximable in this triangulated category. If for every epsilon bigger than 0, we can find an epsilon net, Y epsilon as before, and we assume that this is a finitely generated subcategory of our triangulated category. Now here, finitely generated is not very precise because depends on what we mean by generation in triangulated category, if it's generation or split generation and so on, but not so important here. And okay, this is our concept of approximability. And yeah, a bit of notation, I will write F epsilon for the generating family of our epsilon net, and I will denote by F the union of all these generating families. And here a little remark which is easy to see is that if our space X is categorically metric approximable in a triangulated category C, then its image in the Grothendieck group is finite time approximable in the sense of Turing here. Okay. And what we were able to prove in our symplectic context is that our metric spaces of Lagrangians endowed with the Lagrangian spectral metric are indeed approximable in appropriate versions of the persistence derived Fukaya category of M. And here, just to give an idea, the approximating family in the case of the cotangent band are cotangent fibers that we add as modules to the derived Fukaya category, while in the case of S2 are just like straight equators that meet in the north and the south poles. And this leads to some more or less immediate consequences. The first is this kind of quasi-rigidity that assume we are in the approximable scenario and we have a compactly supported Hamiltonian in our manifold. such that for some epsilon bigger than 0, this Hamiltonian preserves the elements of the generating set as sets. Then we have that this Hamiltonian cannot move any geometric Lagrangian. Here L is X. It cannot this Hamiltonian diffeomorphism cannot move any Lagrangian in the spectral metric by more than a uniform constant time epsilon. And this we might have some relations with the Viterbo conjecture. Maybe I will say something after. And another corollary is that in these approximable scenarios, then there are meaningful notions of entropy for maps sending Lagrangians to Lagrangians induced by Hamiltonian diffeomorphisms. And here, and this is like in like the way we do this is that we introduced a weighted version of a notion of categorical entropy introduced for endofunctors of triangulated category by Dimitrov, Aiden, Kazarkov, and Kontsevich. And we are able to prove that this is related to the Barker entropy introduced by Cinelli, Ginsburg, and Gurel a few years ago. And also about this, I will say something later. And as a consequence, actually, as a consequence of the definition of the notion of categorical entropy for Hamiltonian diffeomorphism, we were able to show that in some cases, like for cotangent bundle of hyperbolic manifolds, but also for the sphere, actually the space, our space of Lagrangian is not totally bounded. And in particular is like impossible, basically impossible to define topological entropies for maps induced by Hamiltonian diffeomorphisms. So the fact that this fails, well, this is true, yes, suggests that this is a more correct notion to like tackle this problem of studying complexity in our metric spaces. And yes, the main tool here are Fukaya TPCs, or what we call persistence-derived Fukaya categories, which I will not go into the precise definition because it's quite technical, but basically starting with your family of Lagrangian, you can build this so-called infinity Fukaya category out of it. This depends on a lot of choices of Hamiltonian and almost complex structures and so on. And this is quite standard nowadays. There is this beautiful book of Seidel. The problem is that whereas Floer complexes are known to be filtered, the higher infinity maps of Fukaya categories are in general not filtered. What I did a couple years ago is to show that if you do smart enough choices and you work with a nice enough model of the Fukaya category, then you can indeed make everything filtered. And then through some abstract nonsense, which is contained in a paper of a couple years ago by Biran, Cornea, and Zhang, you can build a TPC out of this A infinity category by like taking your infinity category, embedding it into the category of modules. Now here you can add fibers if you work over cotangent bundle, and then you complete with respect to cones, with respect to filtered cones, and then take the homology of this category. And what you get is TPC, which is a category where morphism between objects are persistence modules and whose zero level, if you consider only filter morphism, if you want, is a triangulated category in the classical sense. And this comes with interleaving distance, which is basically a categorification of the notion of interleaving distance between persistence module. And here the basic fact is that in our case of the Fukaya category, if you take this interleaving distance and you restrict it to the geometric Lagrangians you started with, then basically you get the spectral metric on the space of Lagrangian. This is an observation containing Guillermo Viterbo and Biran Cornea Zhang. And yes, so yes, I called our persistent derived Fukaya category by C. And yes, there are just a couple construction that C comes with two subcategories, which are both triangulated. C0 is the category I was talking about 1 minute ago, is the category same objects, but with zero shift morphism only. And C infinity, which is the category where the objects are the same and the morphism, their infinity level are the infinity level of our persistence model. And this is what Biran, Cornea, and Zhang show. This is triangulated equivalent to the classical derived Fukaya category. And so at this point we can rephrase our main theorem about that was like our metric spaces are approximable in these persistent derived Fukaya categories. And the statement, the equivalent statement is that for every epsilon, we can find a finite family of objects in this huge persistent derived Fukaya category, such that for every object in curly L, that means for every geometric Lagrangian we started with, there exists another object in the persistence derived Fukaya category, which I call L epsilon, which is a iterated cone over morphism, over filter morphism between elements in this finite set F epsilon, such that at the end, what you have is that the interleaving distance between the geometric object L and this cone is smaller than epsilon. This is just what we proved. And this allows, as I was saying, the first thing that one of the first things one can do is like try to refine every like complexity measurement for triangulated categories to this setting. And one can define, for instance, a weighted version of this categorical entropy introduced by Dimitrov and friends, which is defined just by looking at the growth of the number of these cones here, at the number of k, when you apply a functor, yes, an Hamiltonian diffeomorphism over and over to one fixed Lagrangian. And what we were able to show is that in cotangent bundle of hyperbolic manifolds, if you choose your Lagrangian and your Hamiltonian diffeomorphism carefully enough, this number for very small epsilon is non-trivial. And this basically shows that your space is not totally bounded. But okay, how did we prove this statement here? Well, for S2 and T2, basically this boils down to weighted version of like this celebrated Abu Zaid split generation criterion, and which says that if the open-closed map defined on Hochschild homology of a family of Lagrangians hit the unit in the homology of the total space, then this family of Lagrangian split generates your Fukaya category. And in our persistent setting, we have that since the Fukaya category is now filtered, then Hochschild homology inherits the structure of a persistence module. And by doing smart enough choices, you can turn the open-closed map into a persistence morphism that is a morphism that respects the filtration. And yes, what you can show is that if a Novikov multiple of the unit in homology or fundamental class in cohomology lies in the image of the open-closed map restricted at level 0, then your family, in this case, retract approximates, which means that in the definition of the interleaving distance, we just take one composition equal to the identity. And this basically means that to hit the unit, you need a certain cost, and this cost is exactly the cost of approximating. And for the sphere, if you take enough straight equators, it's not hard to see that the open-closed map counts like slices as this, so that if you take enough equators, you can make this area smaller and smaller, and at the end you get that the image of the cycle, the Oxford cycle corresponding to North Pole tensor south is exactly the area of this slice times the fundamental class. While for cotangent bundles, things are maybe a bit more complicated and is based on this idea used by Biran and Cornea in their paper about Lagrangian cobordism in Lefschetz vibration, that where they basically, in this case, approximation boils down to an argument that says that if you embed the disk bundle in a Lefschetz vibration, you can disjoin your Lagrangian from fibers via a sequence of then twists, and then it uses a very quite delicate quantitative argument on the displacement energy of the Hamiltonian that you need to displace this disjoint Lagrangian from the disk cotangent bundle into in your Lefschetz vibration, and this is based on, yes, this what I wrote here is based on recent work by Giroux and a student of his, Zrekovic, which where they construct a very delicate Lefschetz vibration where you can like have nice control over these quantitative measurements. I think I'm already over time, so I just I think I will finish here.
Thank you. Giovanni, any questions?
So you had this notion of finite type approximation, with this approximation with finitely generated group. And
yes.
What is known, I mean, for instance, for Hamiltonian diffeomorphisms with Hofer metric or hydrodynamical metric. So is there a chance for such thing?
I think nothing. So one, I mean, I think Octav can agree with me here. I have no idea how to like extend all this work that we do to the Hofer metric, because it's not clear how to see it in the derived level.
Interesting.
Yeah, I mean, here I sketch some future direction. This is, yeah, exactly this. I don't know, maybe using some, I don't know, they have this paper, Lagrangian Pictionary, where they work with immersed Lagrangians. I don't know.
So, Leonid, I think even, so it's a good question, even in general. In other words, let's forget the Hamiltonian group. So let's think about other, other groups of diffeomorph, whatever, you know, various groups. what is not hard to prove is that many of the groups you would sort of naively hope to be like, you know, maps into from the interval to R, or with different types of topology. These are not finite type approximable. It's not hard to see.
So let's say diffeomorphisms of circle with hydrodynamical metric or something like this.
Okay, well, it's very, so the expectation is that most of these groups are not finite type approximable, but I don't believe the problem has been studied. So
Fantastic. Okay.
yeah, I know. I mean, I agree with you. I also felt it's like a hole there somehow, that maybe it's interesting to dig more in. But what is certain is that the natural reaction when you look at this is to say, well, but I know Fourier approximations for functions. So there or polynomial approximation. So there I approximate each function by a finite length polynomial or series, right? But the length is not the same. I mean, the type of, it's like, what is this finite type approximation would mean that I have some finite family of generators that are good for all elements in my group. The number of generators should not depend on the element I want to approximate. So that's why things like Fourier analysis and things like this don't work, because there you have different number of, you know, you have an infinite basis of generators. You have to use many of them to approximate epsilon close. But in this definition, if you fix the epsilon, you should have just a finite number of generators that are epsilon good for all your elements in the space. So this is like the, so in fact, from my perspective, is that symplectic result is quite surprising if you look through this definition fully. And what's happening, as Giovanni said, it's a very good question what's happening for the Hamiltonian group.
Giovanni, can you show this slide with further directions, which you did not tell us?
Yeah, this is just sketches. So, I mean, it would be nice to look at further example of approximal dual spaces of Lagrangians. I mean, I think first ideas like spaces of cobordisms. And then one thing that is pretty natural, especially looking at the proofs, is like how to do this with wrapped Fukaya categories. And here there is a technical gap that I never really sat down and tried to solve, is how to define filtered wrapped Fukaya categories. It might be easy, but I don't see it like straightforward. Yeah, what I'm doing right now is looking at Hochschild of barcodes of Hochschild homology and cohomology and how this relates with known quantities. For instance, it's not hard to see that you can see spectral metric as a boundary depth there, but this Hochschild barcode seems to have a lot of bars that I cannot make sense of at the moment. And then, yeah, this offer problem, and I don't know, with Paul, we thought about some, like, I don't know, you can now build Cayley graphs of Lagrangians, I don't know, like random walks here, and how this depends on epsilon and so on and so on.
Thank you very much. Very interesting.
Okay, so thank you, Giovanni. Thank you for all the speakers today.